actually, well, I don't really need to work on column J because I know what it's going to be. So Rij is going to be 0. Ri minus 1j is going to be the square root of sum of squares of these two elements. But I'll go ahead, just for simplicity, and have us work on columns j through n, because technically that's just the part of the matrix effectively changing. I don't need the other columns, because anything to the left in these rows is already 0. So I don't need to touch those. It's important to keep in mind, make sure you're not operating on 0 entries, because that's just inefficient. Okay, so now R is updated. The last thing I need to do is update Q. Now for Q, I'm rotating columns I and j. So I'm going to work on all rows, so 1 to m, and then columns I minus 1 and I. Right, so this is a MATLAB notation. The colon operator implies a range. So I'll take those columns and multiply on the right by this matrix, not transposed, to perform the same column rotation that I use as a row rotation over here. Okay, so that goes ahead and updates Q, and then I'm finished. Okay, so I'll need to fix this in the notes, because in the notes I was using this, but that's not what I need here, because that makes it look like I'm using rows I and j to update the element ij. I am changing the element ij, but I'm using the row right above it to do that. And this was not, this matrix is not conveying. So I'm not using this matrix in this algorithm. So I could rotate any 2 rows or columns that I want using a given rotation by doing something like this. As I said, in this algorithm, I'm always rotating 2 consecutive rows or 2 consecutive columns. So here I'm just focusing on the appropriate rows and columns. Questions about the algorithm? And now I'll fix the notes.
Do I need to mark out that matrix altogether?
Yeah.
Yes.
Oh, mark it out in the notes?
Yeah, like is it wrong or?
This is introduced earlier in the notes, and back then it was useful. It's just not needed here.
So this given this function basically just says it returns c equals x over square root of x squared plus y squared, and that's the square root of 1.
Mathematically, that's what it does. But remember, at the end of class on Monday, I showed how to do it in a way that avoids overflow, and that's what it really does. But yes. Okay. All right. So this is one way of computing the QR factorization. So at the end of this, we'll have A equals QR, and this is given rotations are probably the most useful tool for computing QR factorization, just because they work on one entry at a time. So for instance, suppose the matrix changes a little bit and you want to update the QR factorization. That's best done using these given rotations, because maybe you only have to apply a few of them. And because each one of these does very little work. So each rotation takes order, well, okay, I need to amend this. This one, the row rotation, takes order n floating point operations. This one we're working on an m by m matrix, so this takes order m. Okay. And then the total number of rotations we need is order n times m. So to compute R, we need n squared m flops, and then for Q, that takes more work, it's order m squared n flops. So it's quite expensive, similar to Gaussian elimination on a square matrix. It takes 2/3 n cubed operations. So this takes, if we're doing this on a square matrix, n by n, it's going to take order n cubed operations. example on starting on page 139 in the notes that I won't take the time to write out here. That shows that you have a 5x3 matrix. The Givens rotations that are used to. So actually, the example goes on for quite a while, up to page 143. It shows every Givens rotation used. So you need 9 total Givens rotations to wipe out all the below diagonal entries in a 5x3 matrix. So you can see how it progresses through the algorithm. Okay. So what do you get? In that case, you get a 5x5 matrix Q. That's the accumulation of all those rotations. And then you have a 5x3 upper triangular matrix R that has 2 rows of zeros at the bottom. Okay, so questions about the algorithm now that, unlike the notes, it's finally correct. All right. So this is one way of computing a QR factorization. And now I'll show another approach. Using householder reflections. Now, so what is a householder reflection? So, householder, Alston Householder was a famous numerical linear algebraist, mostly active like in the 60s and 70s. So a householder reflection is a matrix of this form. P is equal to identity minus 2 times V transpose. So remember, if it's V transpose V, that is a dot product, that's just a number. But V transpose, that's an outer product, which is a matrix. And V has to be a unit vector, so it's 2 norm is equal to 1. All right. Now, a matrix of this form has some interesting properties. So, for instance, suppose I compute P transpose. So that's going to be identity transpose minus 2 VV transpose transpose. Well, the transpose of identity is just going to be identity. Now, here we have a transpose of a product. The transpose of a product is the product of the transposes
In reverse order.
in reverse order. So what's that going to give me here?
Then you'll have V transpose.
Yeah. So because V transpose transpose is just V, and V transpose. So P transpose is the same as P. So we can say that P is symmetric. Okay. Now, if I go ahead and compute P transpose P, well, P is P transpose, so that's the same as P squared. So that's identity minus 2 V transpose, identity minus 2 V transpose. So now I'll FOIL this out. So I get identity, times identity, and then I get minus 2 VB transpose times identity, minus this 2 VB transpose times this identity, plus 4 VB transpose, VB transpose. Now, if we look at this, okay, so these middle two terms can be combined. So 4 VB transpose. Now, here I have VB transpose, but if I group them like this, I have V transpose V. So I have a dot product in the middle of an outer product. But in this case, what is V transpose V?
Is V, what do we know about V? Is it?
Well, look at the board.
It's, with the two norms? Yeah, is it
Yeah.
1?
So V transpose V is,
1.
yes. What?
Is
Yes.
one.
Yeah, because V transpose V is the dot product itself, which is a 2 norm squared,
Which is just 1.
which is 1. So, so what's left is plus 4 VV transpose. But then these two terms are going to cancel out, and we're left with identity. So P transpose P is identity, which means that that P is also orthogonal. So this is rather unusual, to have a matrix that is both symmetric and orthogonal. So if we put those two relationships together, well, the first one says that P equals P transpose, but the second one says that P transpose equals P inverse. So in other words, a householder reflection is its own inverse. That's something that you wouldn't expect. You might think, well, what matrix is its own inverse? Well, identity and minus identity, but so is this one, or any matrix of this form, which is quite convenient in cases where you need an inverse. For instance, householder reflections will be quite useful when we go to compute eigenvalues, because we want to take a matrix and apply like P inverse AP. Well, P inverse is P, so that so you don't have to do anything to get the inverse. Okay. So this is one very important aspect of household reflection, symmetric and orthogonal. And we want orthogonal matrices for purpose of computing a QR factorization. But the next thing I want to discuss is, why is it called a reflection?